Well, thank you all for joining while we're waiting for the web conference here to connect. We're going to talk about using the Sinda Thermal Analyzer for electronic packaging. Traditionally, Sinda is used in the aerospace world, but other industries as well, including the electronics industry. And people who are in the aerospace industry run into electronic packages a lot. Avionics on airplanes and spacecraft have electronic boxes and things. Let's see, my screen all went blank now, so I assume it's getting ready to share. So we'll look at how we can use our Sinda plugged into Patran modeling tool to build models of electronic boxes, PC boards, things like that. Okay, I think it's coming up. Let me pull up my PowerPoint. Okay, so Sinda itself is a thermal analyzer, and it will basically read an input file, a text file, input file, and write out a text file. So it's kind of text file in, text file out. But the way people build models for Sinda, traditionally people have used text editors and built these network models, or we have our own Windows GUI called Thermal Studio that comes with Sinda. And then some people like to use what we call our Office Toolkit product, which gives you a Visio or Excel link to Sinda. And there you can kind of make more of a graphical model. And Sinda is a network thermal analyzer. Thermal models are built with thermal masses and thermal conductors modeling heat flow as conduction, convection, and radiation, or advection or fluid flow. M-dot sort of fluid flow in pipes or over between PC boards or natural convection. So we can model the various types of heat transfer using the Sinda conductors. So it's really called a lump parameter finite difference code. It's different than a finite element code, and the people in the aerospace world have been using Sinda or a code like it since about 1962, and it fits the aerospace advanced thermal needs better than the FEA codes, and that's why it's so popular in this world. We also have a modeler called Thermocode to put things in orbit, to do orbital heating, and that will connect with Patran that can build the satellite models, or you can just use Patran by itself. And Patran interfaces with a module called CindaRad, which will compute view factors. We'll talk about that in a minute. The Thermal Studio is the GUI, the Windows GUI for Sinda, and it helps expose the features of Sinda because Sinda is more than a thermal analyzer. It's really a thermal programming language. If you don't have a feature in Sinda that you need, type of heat pipe, type of heater controller, you can just add Fortran logic and subroutines or other languages too. You can in LinkedIn, and so it's really a thermal programming language. It's been an industry standard for. It's coming up on. Actually, this year it is the fifth decade, 50 years since 1962, when the founder of MSC Sinda, the originator of this variant of Sinda, wrote CAE during the Apollo program. And users can add programming logic, like just a simple if-else-then statement. They could add a simple equation, like a convection equation, or whole subroutines, and you can learn to do that in a few hours. It's intuitive and pretty easy to do. So it adds a lot of flexibility by giving you that programming capability. You can start using Sinda after only about an hour of training, and it does have a nice Windows GUI, but it also transparently integrates into Patran for doing 3D geometric models using CAD, as we'll see in a few minutes. So let's look at an electronic package, and let's look at the simple approach, what we call our network thermal model, and then we'll look at a more detailed finite element model that's generated in Patran, but still using the same solver, Sinda, in both cases. On the model on the left, it's a simplified model of this electronic box, and this box was a pressure vessel, the top's removed, and inside this pressure vessel was a little frame that was shock isolated. It had 8 hard drives from laptops and a motherboard. And this was a data storage device used on a Air Force satellite, and it was, I was told, the first time they ever flew hard disk into space on a recording instead of magnetic tape like they normally use, or memory. So they were using just off-the-shelf hard disk. And we needed to get the heat out of this package into the frame and conduct down to the base that was mounted on a radiator in a satellite. And so I cut this right in half, this frame, and built a simple network model just to see what was happening. Wanted to see if I was going to get my energy out of these hard disk through their mounting resistance through the frame and out through the shock isolators. And I found out we couldn't really get the heat out of it, so we added some braided copper straps that I modeled here, and I sized and figured out how many straps I was going to need in order to get the heat out of it. And we had a power duty cycle, and we looked at our transient thermal responses and pretty much figured out the temperatures and temperature responses of this package just from this simple 20-node model. Then build a detailed model, which is always nice eye candy for proposals or presenting to the customer. They always like a colored picture. Even if the answers are wrong, a color picture really impresses people. But by having this simple model, I could check the more detailed model to make sure that it was giving me the right answer. If you just start with the detailed model, it may be very difficult to know if you have the right answer. So the nice thing about Sinda being the network approach, a real intuitive approach where you have thermal masses for this drive, like watt seconds per degree C. So if I know you put so many watts in here for 10 seconds, it's going to go up so many degrees C just by knowing that thermal mass number, or the thermal contact of conductors are degrees C per watt. Or watts per degree C for conductors. And so by mounting it, and if it's like 10 watts per degree C, I know for every 10 watts that flow from the disk drive to the frame, there'll be 1 degree C gradient. So the Sinda thermal model makes a lot of physical sense and gives you insight into a thermal system. So we encourage people to either use Thermal Studio and a text editor, or use a Visio-like tool which builds a Sinda model from this diagram automatically and then launches Sinda. Use a simple tool like that to get started on any model, whether it's electronics or whatever. But we do plug Sinda into Patran, and it's transparently integrated and has a thermal preference, so it doesn't look like a structural code. It has a thermal look and feel, thermal loads, thermal materials. Radiation can be solved with either MSC Thermica, which would do the orbital heating, or even terrestrial applications or planetary applications, where you put something on a planet like the Earth or Moon, and we can do the sun moving overhead and heating it. And then we have our CindaRad product that I'll give a brief demo on at the end, and that is a very fast view factor solver where you can do millions of view factors in a minute or so. So it's a very fast view factor solver program. And then the full programming power of Sinda is still available even though we plug it into Patran. You can still add equations and programming logic right into Patran interface. Here's just an example of a model of a vacuum oven where we actually had a very complex controller on the final model we built with multiple zones of heaters and sensors and PID-type controllers, and had hundreds or maybe thousands of lines of programming logic in order to model this complex heater system with feedback from multiple zones to see if we could hold temperature very accurately of things placed on that plate. So now let's look at a couple things about thermal modeling in general. Some things that are very important in thermal modeling are you need to model conduction in joints or interfaces. This might be a card guide and a PC board attached like through a wedge lock to the chassis. Could be a component mounted on a board. But these joints or interfaces are very important in thermal models. And you might have a good structural joint, but you go up to high altitude in an airplane, get 40, 50,000 feet, or you go into space, and those conduction through those joints might disappear as that little air gap, that's a little air in that joint becomes very, very thin or disappears completely in a vacuum. So modeling joints is very important. Modeling convection without going to a full CFD code, because Sinda runs in tens of seconds or minutes and occasionally may go for hours, but usually it's more like minutes or tens of minutes, where CFD codes go in hours, tens of hours, or even days, and are very slow. And with CFD, if you don't it's very hard to test verify a model to adjust the convection to get a test in a lab to agree with your model if you need to test verify it and adjust things, because you kind of get what you get as far as the convection, where when you're using your own convection correlations, you can adjust those to help get a test verified model. And then modeling thermal radiation is important. And that can be difficult because of the large number of view factors, but we found a way to handle those in an electronic box where you can have multiple PC boards and components and a very detailed CAD-like part and still be able to handle the radiation. So let's look at how we do contacts. We have thermal contacts built into the product, and there's three types of contacts: edge to edge, edge to surface, and surface to surface. Here you see this plate and this plate are connected by edge to edge, and you can see those little lines showing how the conductors are all hooked up. And then we have surface to surface. The bottom of that cylinder is connected to this plate. It actually projects the bottom onto the plate, and we do these contacts. You can do them with nodes and elements, but typically we do it with geometry, and you can do it even before you mesh if you want. And we're really hooking geometry to geometry, and then when you mesh it, it will find the right nodes and to hook up for your contact. So we would take the disk on the bottom, that surface and this surface, and say those are my two surfaces and give it a contact coefficient, or this edge is connected to this surface. And if I happen to move that plate somewhere else, that contact is still valid. It will hook it up at runtime. It will project the edge of that plate onto the surface and hook up the right nodes. So you don't have to make sure your nodes are lined up, or you don't have to make sure you have congruent meshes. We hook it up mathematically as correctly as possible. And just a little bit about that math, although it's more difficult than I understand, actually, how we do that. One of our developers spent quite a bit of time coming up with the algorithms. But the way you can visualize it is like below that disk there, that disk that's connected to this big plate. It's as if we would put a material in between and do a tetrahedron mesh on that, just mesh that material and allow heat transfer to only flow perpendicular to the joint. By doing that, we eliminate some potential errors. Same thing on the edge to edge. It's as if we filled that gap. They could be touching, or you can leave a little gap. It doesn't make any difference. A lot of people like to leave a little gap just so the nodes don't accidentally get equivalents and you get a hard conduction. But we only allow heat transfer to be perpendicular to the joint, which eliminates problems if you use a simple method like closest node method. The other thing we do with contacts are we can do advection. We can have external flow like m dot of the air, mass flow of air through an electronic box, or an external flow over something, over a box or over an automobile or airplane or whatever. And then we can say tie that airflow, which is just modeled with flow tubes, 1D conductors, and tie those flow tubes there to the whole surface here. And we don't have to pick nodes or elements. We can just pick the geometry and pick the surfaces that form this whole plate here and say, take all these surfaces and tie it to that airflow, and it will automatically hook up every node on this surface to the nearest air node and do an HA conductor and do that automatically. So whether it's external or internal here, it will make sure your entire wall is hooked up, and all you do is specify hook up this whole wall of this tube to that curve that models the airflow down the middle. And so you can do it on a geometry basis, and then if you remesh, it will redo the hookup at runtime. And we do have visualization, as you can see, of these conductors, so you can see where they're a contact or a fluid HA conductor. We can visualize those. You can turn them on and off just to see how it did hook them up. Now, to model convection, some people use something like XFlow, which MSE can provide. And here's a model of an electronic box, and CFD codes are sometimes used for electronic packaging, but they tend to be very slow and take hours or many hours to run. This is, should start flowing a little animation here. And you can see you get a lot of detail on the airflow, and you get a great understanding of the airflow, but they're usually pretty weak when it comes to the thermal side. If you have to add a heat pipe like they have on a laptop motherboard, they use heat pipes going from the CPU chip to the little finned heat exchanger and trying to put that logic in, which is a one-way flow, and it's flow limited. Even if the delta T gets higher, it limits the Q through the tube. To put that logic in is pretty trivial in Sinda and generally not possible with CFD code. So again, you can't adjust your convection either. You got to take what you get. So there's another approach we have, and that's to use built-in correlations. We have about 40 of them, or you can add your own. The standard Nusselt, Reynolds, Rayleigh number correlations you'd find in any heat transfer book, which are based on experimental tests. These correlations sometimes give very good results and sometimes give adequate results. So while we're not a replacement for a CFD code, many electronic packages can be modeled using a more simplified approach, and then your model runs in tens of seconds instead of tens of hours. So here's one of the correlations we have, which is internal flow in a circular duct, and it uses a Nusselt number and then computes the H from that. And here's a little more complicated one where we have natural convection off of a vertical surface, and here we have to compute a Rayleigh number, and we have Prandtl number here, and Rayleigh number to get the Nusselt number, and then we get the H. It's math algebra is a little messy, and it's difficult to do by hand. But when you use it in Patran, all you do is pick air out of your material library and give a characteristic length of like 1 meter or 0.2 meters for that vertical surface, and it will do everything for you, and it will compute the H, which is a delta T dependent value. As the surface gets hotter, the H will go up. That delta T between the surface and the air affects the H value, and this is automatically computed and automatically changing. So the way in Patran you would add advanced convection, it's really almost as easy as just doing simple convection where you'd guess an H value of 6 or 10 or something. All you do is you come in and say what units you want to work in, and you go to our material library, which is just an Excel file, Excel template that we provide, and you can add your own materials, and you can make them temperature dependent like this air is here, where when you say apply, it will bring this into Patran as an air material. It'll bring in all the tables and put them in as fields, viscosity versus temperature, density and conductivity versus temperature. Or you can have a fluid in there that just has constant properties. One's not any more difficult to use than the other one. And then we pick out of our correlations what correlation you want to use, natural, external forced, internal, laminate, turbulent, or transitional. You pick that, and there may be some data, like for natural convection, we have to provide a characteristic length, and for like flow between two parallel plates, which might be two PC boards where you have airflow in between them, you would have to give a hydraulic diameter, a cross-section of that passage, and then the mass flow rate of the air flowing through. And once you do that, it produces a correlation for you that you just attach when you put your load on there. Instead of putting a constant H value, you just pick that correlation from a list and it attaches it. So it's really as easy to use in a load like natural convection on here is picking a hardwired number. And here, this is one of the training materials that we provide, one of our workshops. We have a PC board. We've mounted the components on with contact coefficients, put power into the components, and we set up natural convection, and we get 55 degrees. And then we put air flowing on both sides of it, like this PC board was in a box with channels, and we put the m dot of that internal airflow and used a correlation, and you see the temperature drop down to 42 degrees, and if you crank up the m dot, it would even drop more than that. So it's pretty easy to add these sort of convection, or you can write your own equations or use whatever you maybe know works best for your application. Here's an example, which is also from one of our workshops, of airflow through these 5 passageways where you put some heat from electronics onto one side of this channel, and that's like a heat exchanger where air is flowing down through there. And we have a curve going right down the middle, and it automatically connects the airflow along from that curve to all the surfaces, all the little nodes on this passageway. So let's look at modeling PC boards, and we'll walk through a simple example. Here's just, this is actually from one of our workshops also. We're putting 8 watts into a PC board. We're fixing the 2 edges at 25 degrees, and we're modeling the board as a thin sheet of copper. And most people model PC boards that way, and they don't go into all the layers because that just adds more detail than is usually necessary. Sometimes you have to look at thermal vias and some effects on a board, but frequently you can just model the board as a thin sheet of copper. And we do that because copper is about 1,000 times more conductive than the G10 or the epoxy fiberglass material. So the conduction in the epoxy is insignificant if you have any copper at all on your board, and most people put copper planes, thermal planes, and things in there. So we're modeling the PC board as simply a thin sheet of copper. Talk more about that later. We give you a little formula in one of the workshops saying the middle temperature should be, in this case, 50.58 according to this formula, and then we build a Patran model, put uniform plate into the same size plate, and we get 50.58 in our Sinda model that's built in Patran. So that's how you can just do a simple PC board, uniform power over it. But the reality is your power isn't uniform. It's concentrated in different spots. So here we have power, maybe a component here, a microprocessor or something. Same power in this board that we have in this board, but it's some of the power is focused on this area here, and we get 58 degrees, or about 7.9 degrees higher than we get down here. So that's the real life is the power is not uniformly distributed, unless you have just a low-powered board with a bunch of small packages on there, signal conditioning or something, and sometimes it is distributed. But when you have a component, a power device, a hot device that may have 5 watts or something of power, the way you need to think about it is you have this component that's mounted to the board, and there's a couple terms you should know about. Theta JC is a value junction to case thermal resistance in degrees C per watt. In this case, I'm saying the theta JC is 5 degrees C per watt. That means for every watt flowing out of here, you're going to have 5 degree C gradient. So 4 watts is going to cause a 20 degree gradient, which you see 86 to 66, that 20-degree gradient. And you get that number from the spec sheets for the device that you have on the board. They'll give you, if it's a power device where you're concerned about the junction temperature for reliability, they will give you that. Then you can figure out what the junction temperature is, which the reliability people want to know from your thermal model. There's also a case to board mounting resistance, and that is usually determined if you put grease underneath or a sill pad, and then it's pretty easy to calculate. If you don't have anything underneath, then you may have to look at the leads and the package and look at some data to see what that particular package mounting resistance is. That's a harder number to come up with. In this case, I just picked 2, so those 4 watts are flowing through here. We get about an 8-degree delta across it. So what some people do is, instead of modeling all the components on the board, they'll just bring in a CAD file and mesh it, maybe mesh it around the components, and then they will put the power in where all the components are and just put it right into the board. And then to get the case temperatures or the junction temperatures, if it's a power device, they will set up like an Excel table. You'll put the device in here like U2 is a voltage regulator. It's 0.95 watts. Theta JC is 4.2, so we know it's going to be running about 4 degrees higher than the case when you have 1 watt flowing through it. And then you come up with a case to board resistance in degrees C per watt, and I just put a placeholder as 10 here. And then you go through your model and you put the temperature under each part. So if I look at each on my board model, if I go to my previous picture and I look at the temperature under each part and see what it is, I can put that in this table here, and then it will use these thermal resistors here to calculate what the case temperature is and what your junction temperature is. So this is a method some people use where they don't want to put all the detail in the board, and you can knock out boards pretty fast that way and even do a series of boards and a card cage, things like that. So let's look at an example where we have this PC board here, and in this case I'm going to put some components on the board and use our contact feature where I just pick the bottom of that component, that surface, and I pick the surface of the board and say those two are tied together with my coefficient that would give me my mounting resistance for that component. And to get the conduction in the PC board, like I said, a lot of people like to use an equivalent copper thickness method. It's a simple method, but it generally works very well. There's a few exceptions. And you look at each of the layers on the board. If you look at the artwork, which you can get for the board, you can just estimate what percentage of copper is on each layer. And when you have power planes or thermal planes, they'll be virtually 100%. In this case, like 92%, about 8% of open space, and it was almost all copper. And they're usually thicker, 2-ounce copper, which in English units are 2.8 mils thick. And you take the 92.92 and multiply by that, and you get an equivalent thickness. If you would melt that copper over the whole board so it flowed 100%, it would then go down to 2.5 mils thick instead of 2.8. And you add up those. Usually you ignore the signal layers, and you just take the ground planes and the power planes and add those up, and I get equivalent thickness of 17 mils of copper on this in this board if you would kind of melt it all down. And so I take my little equation that I have and I put in the power into the board, and I can estimate that the board's going to rise in the middle about 1.7 degrees based on that thickness of the copper, conductivity of the copper, and the dimensions of the board. So that gives me an idea what to expect. And so I like to, before I put all the discrete power where it's located in the chips, just put that uniform power on the board and see if you should get the same answer. And I did. I got 1.72 degrees. I fixed the edges at 0 degrees, got a 1.72 degree rise, which is exactly what I was expecting. So that tells me I haven't messed up my thermal properties or dimensions or units or something. So you always should be checking things. And now we'll go through and put the power into the individual components. And then if you look at the board now, under the components, you'll see it has some hot spots where the higher powered components are. And if we just put those temperatures into our table here, we could compute what the case and junction temperatures are, and we see we should be getting around 12 to 13 degrees for that hot device. And when I look at my Patran model and actually put the power into that device, I'm getting 13.3 degrees. So it agreed with the board method where you just put power into the board. But this way I can look at one group of just my components, or I can look at my board and see the temperatures and get them out a little more directly. So a couple different ways. You can go to different levels of detail. You can even put a theta JC and a little plate on top to represent the junction if you want, but most people don't go to that detail. So now if you have these boards and you want to put them in a box, you can put multiple boards in a box. You can have card guides like wedge locks or something on the side. You could have a lid that has mounting conductance in a joint of some sort that might have an O-ring. We have natural convection in here, and we have venting, so we have an M dot sort of flow coming through this box. And we have radiation on the inside and outside, and we have contacts between the components and the card guides. And let me just drop out here and show you this model. Right before I do, I want to make one comment on Sindarad and how it works, because I said we can do radiation even with very large, massive models. And so I'm going to just actually run this. I have in my thermal solution Sindarad selected as my solver, and I also picked to run it interactively. If I already ran Sindarad, I could say reuse existing results, and then it wouldn't run it again, and then I could rerun the model and change maybe powers into the model. But I want to run Sindarad interactively to show you how we compute these view factors and how fast we compute them. There's about 11 million view factors because every surface on the inside sees every surface, and I just meshed this pretty finely and didn't take any care in making a coarser mesh on this aluminum box. So it drops into my Sindarad interface, and I'm going to hit compute here, and you can see a little green scale going across. It takes about 60 seconds to calculate about 11 million view factors. The one thing I want to tell you is if you're a Sinda person, you know that we have conductors that go from node to model radiation conductors. So normally the traditional Sinda approach, we would have to put 11 million Sinda conductors. And while that's possible, even with the old 32-bit Sinda, we could do models that big. Now with our 64-bit Sinda, we can do very big models, but it would run more slowly. It would take a while to pre-process those 11 million conductors. So with Sindarad, we have actually two different methods. We have a method called a flux method, and we have a method called the RAD-K, which will produce 11 million conductors. I'm running the flux method here, and what that means, instead of putting in the conductor itself, we'll put the effect of the conductor. We'll look at the energy flowing from one face to another face by looking at the geometric view factor, the emissivities, and the current temperature, and we'll calculate how much energy leaves one surface and arrives at another surface. So let's get back to our Sindarad, which is finished by now. And I want to just show you that in Sindarad you can explore how the view factors. I can look at the view factor from here to here and get a picture of what it looks like. So if you have something hot and you're wondering, is that real hot device, that transformer, is that going to be shining on a board? You can just kind of look at the model and play around. And when you're done, you just close it. And it will, I'm going to save the results. It will fold the results into the Sinda model, and then Sinda will start running. And this model, even though it has 11 million view factors, you'll see it runs in just 5 seconds or so here. It's running now with our SSQRM, our quasi-minimized residual method, which is a very fast method for radiation problems like this. And we also have conduction in here, and we can bring in our results and and then look at the temperature results of this. This model. And then quickly, I'm just going to show you this other box with PC boards in it so you can see what that looks like, and then we're finished. So this is a little more complicated box level model. You can work at a component level, you can work at a board level, box level, or even a whole aircraft like a J-Star sort of plane full of racks of equipment and airflow through all these racks. So I've made a lot of groups here on this model, and I can look inside of it. I've got a group that kind of lets me look inside and see what it looks like. Here we can see the couple PC boards with components. I can actually look at the some of the contact. Look at those two groups together, and I can see the contacts that are below the components and how the component's hooked to the board. Where if the component goes outside of an element, it will hook up some weak conductors even out a little further to make sure it gets the right energy into each element. We also have contacts for the card guides, which you can see these cards were not lined up exactly with a row of nodes, and so it split the energies going out into those two to give the right power into that connection where the card guide would go. So this shows you a little bit what we do with more complicated models. So now let me pull my last slide in here to show you what software we used during this demonstration. We used Sinda as a thermal analyzer. We used Patran as a model builder with the Sinda plugin, which gave us a thermal interface with all thermal materials and loads. We used CindaRad to compute the view factors, and it does run on multiple cores. I only had 2 on this machine. If I run on a 4-core processor, it will run even faster. And then we do have all of these packaged together into something called MSC TFEA, which is a very cost-effective product that you get a version of Patran, a thermal-only version of Patran. You get the whole package for far less than just a copy of Patran. So you can get a nice thermal package called Thermal FEA. And we call it FEA because Patran's an FEA modeler, breaks things into finite elements. We end up turning those into a network model that we really solve. And then if you already have Patran, we have a Sinda for Patran plugin that includes Sinda, the preference for Patran, and CindaRad. So there's a couple different configurations. And come with Sinda, you get about 14 workshops modeling convection. We have some with PC boards. We have thermal distortion or thermal stress. And if you have any questions on electronic packaging or modeling electronic equipment, you can get me at ron.behe@MSC Software.